There's, I want us to look at the isomorphism of elliptic curves. And this, what we'll be doing is, supposing you have an elliptic curve and you want to map it to another elliptic curve. You want to see how to map the elements of an elliptic curve to elements of another elliptic curve. So that's what we'll be doing. So what I'm saying is, if we are given two elliptic curves, E and E prime, when do we say that these two are isomorphic of a field? When do we say that they're isomorphic? So we say they're isomorphic if one, they are injective, and two, they are surjective. So I'll explain what these two terms mean, injective and surjective. Now, so supposing I have this set with the elements X, Y, and Z, and I have another set with the elements 1, 2, 3. What do I mean by injective? Injective means that the mapping is 1-to-1. What it means that every element will be mapped to one element. Every element is mapped to one element. So we say that this is injective. So for instance, you can see X has been mapped to 1, Y has been mapped to 2. So we don't have an element that is mapped twice. Look at this other case. This other case is where I have X, Y, Z, and then 1, 2, 3. I may have X mapped there, and X mapped here, Y mapped there, and then Z mapped there. So you can see that I have one element that has been mapped twice. So this is not a one-to-one mapping. One-to-one means that every element has one image. Every object X has image Y, 1. Object Y has image 2. Object Z has image 3. That's what I mean by one-to-one. So we can either call it one-to-one, or call it injective. So that is what we mean by injective. And then what about surjective? Now, look at the set from which you are mapping. This is the set from where we are mapping. We are mapping from this set. Every element of this set has been mapped. Every element of this set has been mapped. X has been mapped there. Y has been mapped there. Z has been mapped there. So when every element of the domain has been mapped, then we say that the mapping is surjective. Surjective. Look at this other case. A case that I have 1, 2, 3, and then I have X, Y, Z. 1 has been mapped, 2 has been mapped, 2 has also been mapped there, but 3 has not been mapped. So when we have the set from which you're mapping, some elements not having been mapped, then this set is not surjective. No, the mapping is not surjective. The other word is onto. Now, so what I mean, therefore, we say that two curves, elliptic curves, are isomorphic if there is one-to-one mapping and there is onto mapping, surjective mapping. That every element of the elliptic curve E can be mapped to another element of E prime. So if you have elements of E and then the elements of E prime. So if every element here must have one image, every element must have one image in this other elliptic curve, and every element must have one image. So then we say that it's injective, and then every element from this set must be mapped to this other set. Every element must be mapped, and then we say it's surjective. So then for these two curves to be isomorphic, we must be able to map the elements of one elliptic curve to the other elliptic curve. And every element must be mapped only once. So that is what isomorphism means. And that is what we'll be looking at. So if you're given two curves, you'll be finding the equivalent element from the other curve. That's what we'll be doing. So I'm looking at these two examples. I have this curve, and then I have this other elliptic curve. And then our field is F. So I want to see how do we get the elements of E? How do we get the equivalent elements in E prime? So that is what what our lecture will be focusing on. So how do we find the other elements of the other elliptic curve? Equivalent elements. Now, so there's something I've written here. I've said for elliptic curves in this form, we looked at this form. For these elliptic curves to form an isomorphism, then I'm using prime for what comes from E prime. So X prime, which is here, you know that it will be written like this. Just a minute. What we have is y prime square should be the same as x prime cubed plus ax prime plus b prime. So and the other one, for the E, it's supposed to be y square is equals to x cubed plus ax plus b. So I'm now getting the relationship. What is the relationship between y prime and y? Y prime coming from this elliptic curve, and then y coming from this other elliptic curve. So what is the relationship? We are saying that to get y prime, there must be some u. There must be some u. So that u is what we'll be looking for. So there must be some u, so that when you cube that u and multiply the y from this y, you get y prime. And that same u, when you square it and multiply by x, it must give you x prime. So that's what we'll be doing. So in short, for us to be able to get elements which are elements of E that are mapped to the elements of E prime, we must be able to get that U. We must be able to get that U, so that U squared times X gives us X prime, and then U cubed times Y gives us Y prime. So that is what we'll be looking at. That's what we'll be trying to find. And what about A and B? You have A prime and then B prime. How do we get A prime and B prime? And again, I've said for you to get A prime, you need that same U that we'll be looking for. You raise it to 4 and then multiply by A. And then for you to get B prime, take that U raised to 6, then multiply by B. That's what we'll be doing. So the most important thing is, how do we get this U therefore? That is what is important. Once you get the U, then you are able to get X prime, you're able to get Y prime, you're able to get A prime, and then B prime. Now, so these are the formulas. In fact, when you are writing the code, to do this, so these are the formulas we'll then be giving the code, and the code does that for us. So the code will be finding out if the elliptic curves are isomorphic. Just give it these formulas. And let's look at this first example. We are given this elliptic curve, and there's this other elliptic curve. Then the question is, are these two elliptic curves isomorphic? Are these two elliptic curves isomorphic? Or can you show that they are isomorphic? So for us to do this, then we need to find out if there is that u, so that if we can get a u, we want to find out if we can get a u, so that u raised to 4 times a gives you a prime. In this case, our a prime is 1. In this case, our a prime is 1, and our b prime is 4. Our a is 1, and our b is 1. So that is what we want. Can we find the u, so that this u raised to 4 times a gives you a prime, and the same u raised to 6 times b gives you b prime? Can we find that? So that is our question, therefore. Mod p. Our p is 5, so we are doing it mod 5. Now, if that u exists, then we say that these two curves are isomorphic. But if that u does not exist, then the curves are not isomorphic. Now, one thing you must remember about this isomorphic from the definition, you must then have discovered that these two curves, since they are isomorphic, they have the same number of elements. That if curve A has 9 elements, the other one also has 9 elements, and so on, so that every element is mapped once. Every element is mapped once. Now, so let's try and calculate to get our u. Using this formula, can you get u? So just write our a prime is 1, and then u raised to 4 multiplied by a. A in this case is 1. So what is u? We want to find out what u is. And then what about b prime? Our b prime is 4. Can we get a u such that u raised to 6 times b in this case is 1? Can we get this u? Now, this u must satisfy these two conditions. That u raised to 4 times 1 should give us 1, and u raised to 6 times 1 should give us 4. We are doing this mod 5. We are doing this mod 5. Now, this one you can try without a code. Without a code, you can try it. You can use trial and error. Try all elements of mod 5 and see which one meets those conditions. Let's try the first one. The first one was a prime, which is 1, u raised to 4 multiplied by 1. So I want to find what is u. And of course, we know we are doing this mod 5. So mod 5 has elements 0, 1, 2, 3, 4. So u must be one of these. We just want to find out which one is it. Take, for instance, 0. 0 raised to 4 times 1. This does not give you 1. So 0 is not a u. U is not 0. You can now try 1. 1 raised to 4. Then times 1. Does it give you 1? And we are doing this mod 5. Now this one gives you 1. What about 2? 2 raised to 4. 2 raised to 4 mod 5. What is 2 raised to 4? 2 raised to 4 mod 5 is also 1. So that will be 4 times 4, which is 16. We're doing it mod 5, that is 1. What about 3? 3 raised to 4. So 3 raised to 4 will be 3 times 3 times 3. But 3 times 3 mod 5, this is 4. Mod 5, because that will be 9. 9 divided by 5, the remainder will be 4. And again, this is another 4. So again, this will give you 4 times 4, which is 1. What about 4? So So that's this one. We are using trial and error. We are trying this, we are trying this. But now the code, if we do the code will just give us, and of course the code will also be doing that, but the code will be faster now. Now, so we are not saying that U is 1. That's not what we are saying. What we are saying is that when we tried 1, we got U to be 1. When we tried 2, we got that. When we tried 3, U was that. No, not U. When we tried U to be 1, this is our U. When we tried U to be 0, we found, this is what we wanted to show. This is what we wanted to find. So we're taking U raised to 4, then times 1. So U raised to, if U is 0 raised to 4 times 1, this gives us 0. So it does not accept, does not agree with what we want. This is supposed to be X prime. No, A prime. It's supposed to be A prime. Now, when U is 1, we get A prime to be 1. When U is 2, we get A prime to be 1 also. And when U is 3, A prime again is 1. I've not done for 4. But that's not the only condition. The other condition is that you also try and check this. So where you get the values agreeing, that becomes your U. Where the values agree, that becomes your U. So let's try for the B prime and see. Just create some space here. Just using trial and error. And of course, when you do the code again, that is the method it will be using. Now again, our U, and then this time we're finding B prime. U 0, 1, 2, 3, then 4. What do we want to obtain? We want to obtain 4. Want to obtain 4 because what we have is that B raised to, no, B prime should be given as U raised to 6 times B. So when you take U to be 0 and raise it to 6, then multiply by B. B is 1. This gives you 0, does not give you 4. Now try 1. This time 1 raised to 6. Then multiply by B. Our B is 1. And this again does not give us 4. It gives us 1. So it does not give us 4. So B cannot be 1. U cannot be 1. Let's try 2. 2 raised to 6. So 2 raised to 6. This is 2 raised to 3. Mod 5 is 3. And this is, again, 2 raised to 3. Mod 5. Again, this is 3. Because this would be 8. Yeah, that would be 8. 8 mod 5, that's 3. Now, what about this? 3 times 3, that would be 1. That would be 1. And that would be 1 because we multiply by 1. So U raised to 6 is 1. Then multiply by 1, that gives us 1. So you try 3 again. So we want to see what's that U. At this time, try 3. 3 raised to 6. This will be 9. So this will be 3. Because this is 9 mod 5. That is, no, 9 mod 5 is what? It's 4. It's 4. 9 mod 5 is 4. And then times 3. That would be 2. That would be 2. I don't know whether you're seeing what I'm doing. Lynette, are you following?
Yes, I am.
Okay. Now let me just erase this again so that we do it for 3 again and see. I'm using some shortcuts which we all know, but let's do it the long way. We're taking 3 raised to 6. 3 raised to 6 would be that. 1, 2, 3, 4, 5, 6. But this one is 9. Eh? Is it? 9 mod 5, that would be 4. So this is the same as 4. Then 4 times 3, that would be 12. This 4, this is 4. So 4 times 3, that would be 12. We are doing this mod 5, so this becomes 2. Mod 5, that becomes 2. So that means 3 raised to 3 is 2. And there's another 3 raised to 3 again, which is another 2. So that is 2 times 2, that gives us 4. And this 4 multiplied by b, and our b is 1, so that gives us 4. So we found that u. We found a u such that u raised to 4 times a gives us a prime, and the same u raised to 6 times b gives us b prime. That u is 3. That u is 3. You can see 3 raised to 4 times a gave us 1, and 3 raised to 6 times 1 has given us 4 that we required. So that is that's a formula you use even when you're writing the code. That's the formula we're using. So you just include this formula in your code, and then you have your code telling you if 2 curves are isomorphic or not. Now, so I had already done this question. But I just wanted to go through the steps so that you see the steps I was using. I said we need to find an non-zero u, mod 5, such that u raised to 4 times a gives you a prime. So u raised to 4 times a gives you a prime. And then the same u raised to 6 times b gives you b prime. So that is the u we're looking for. So I said by testing this, we find that I found 2. I did not test. Did we check 2 properly? Let's see. 2 raised to 4. 2 raised to 4. Okay, it must be the smallest u. 2 raised to 4. This is 4 times 4. Mod 5. This would be 1. Eh? Yeah, that is 1. What about u raised to 6? Let's again try. I did not try it properly. 2 raised to 6. 1, 2, 3, 4, 5, 6. Let's try this. That means we did not try it properly. This is 8. Is it? That is 8. Mod 5, this would be 3. And this is another 8. Mod 5, this again would be 3. This is 9, which is again 4. Yeah, that is correct. So I think when I was testing for 2, I didn't do it. This is 3 times 3. Why did I say 1? It's supposed to be, what is 9? 9 mod 5. 9 mod 5, that is 4. That's correct. This is correct. That's how you test. So that u exists. That u is 2. That u is 2. Of course, we take the list of them all. Sometimes they could be several, but we take the list of them all. the list of those u's. If the u exists, there are cases where the u will not exist. And if that u does not exist, then we say that the elliptic curves are not isomorphic. So we say, therefore, the curves are isomorphic because we obtain u to be 2. Now, so the other question that will be the question that will follow, therefore, is that which element will be mapped to which one? Which element of curve A would map to which element of curve B? That is a question that follows, and that is, we'll look at that later. We'll look at that one later. And let's look at another example. Consider these two curves, and we want to see whether these two curves are isomorphic. We are doing it mod 11. So of course, we're just using our formula. And our formulas are here. So we want to see if a u exists such that this u raised to 4 times a. In this case, our a is 4. Our a is 4. And our a prime is 5. A prime is 5. And also we have our b. Our b is 3. And our b prime is 9. Our b prime is 9. So we want to see if this u exists such that these conditions are met. So that's what we want to test. If that u exists, then we say that the curves are isomorphic. But if it doesn't exist, then we say that they are not isomorphic. So I've said we need to find an zero u mod 11 such that this is true and this is true. So when you test all of them, I found that u is 3. When you test all of them, we are testing 0 to 10. Testing 0 to 10. So you find that u is 3. So since u is 3, then we say that two curves are isomorphic. Let's just verify that 3 is the u. Let's just verify that very fast. Go back to our formula. Go back to our formula. Our a prime is 5. And then you have said is 3. I said yes, u is 3. If you test the other elements, you found that they will not satisfy. So it's only 3 that I found was satisfying these conditions. So 3 raised to 4, then multiplied by a, our a is 4. So I want to see if the right-hand side equals the left-hand side. So 3 raised to 4, this is our 3 raised to 4. We are doing it mod 11. This is 9. Now, to make your work easier, we work with the smaller numbers. 9 mod 11, we can write this as as -2. That is 9 mod 11. So we're just asking if 11 were to go into 9, what will be the remainder? So the remainder can still be -2. And again, this is another -2. So -2 times -2 gives us 4. So 3 raised to 4, therefore, is 4. 4 times 4, that will be 16. And we are doing this mod 11, which gives us 5. That gives us 5. So it's easier to work with the smaller numbers. That's why I opted to use -2. Otherwise, you would have gotten 9, then multiplied by 3, that will give you 27. 27, reduce this mod 11. When you reduce this mod 11, you get a 5. Because of 22, you get the remainder is 5. Then this 5 multiplied by 3, that gives you 15. 15. So you have 15. Is it 15? As a mate. This was 3, 3 times 3, 9 times that, 27. 27, 11, the remainder will be 5. 5 times that, that's 15. Okay, that's 15. 15 mod 11, that would be 4. So that means 3 raised to 4 is 4. 3 raised to 4 is 4 mod 11. Then multiply that 4 by this 4. That gives you again the same 16 mod 11, which reduces to 5. So I'm just verifying that the 3 that I chose on was correct. But of course, how do you get 3? You're trying all values of u, 0, 1, 2, up to 10. You're trying all those values up to 10 and seeing which ones would satisfy those conditions. You can also try and see whether this other one is satisfied. B prime is 9, and u raised to 6, and then raised by multiplied by b. So you want to see whether the right-hand side will give you the left-hand side. So the right-hand side is 3 times 3 times 3 times 3. These are 6 times. 1, 2, 3, 4, 5, 6 times. We are doing it mod 11. So as we had done earlier, this is 9 mod 11, which is -2. It's another 9, -2. It's another 9, -2. So -2 times -2 gives you +4. Then +4 times -2, this gives you -8. We're doing this mod 11. And since we have a negative value, just add 11 to it to get, is it 3? Get 3 mod 11. Yeah, we are only interested with a positive value. So when you add 11 to that, you have -8 plus 11. That gives you 3. So that means 3 raised to 6 is 3. 3 raised to 6 is 3. Now multiply by this 3 and you get a 9. So it means that the right-hand side equals the left-hand side. So that therefore means that the two curves, since the conditions have been met, the two curves are therefore isomorphic. Now we look at the last example. Of course, the knowledge of isomorphism of elliptic curves is very important in cryptography, and of course, we look at how it's used in cryptography, how important it is. And let's look at this one. Given this elliptic curve, you can identify A. Our A is that, and our B is this. Our A prime is that, and our B prime is that. Question is, if they're considered mod 13, would they be isomorphic? These two be isomorphic. So I want to check values of u from 0, 1, 2, all the way up to 12, and see whether you can get any value of u that fulfills this condition and this condition. So both conditions must be met for it to be the u we are looking for. Not just one condition, must meet both conditions. So we try all those and see whether we can get this one value that meets those conditions. . Now, when I tried all of them, when I tried all those values, and of course you can do that later and see whether you get the same result as what I got. When I checked all those values, I discovered that none of them will meet those two conditions. There was no U. There was no U that would meet those two conditions. Therefore, we would then say that these two curves are not isomorphic. These two curves are not. Okay, so before we go to how to write the code for this, why are we looking at isomorphism of elliptic curves? And I've said their knowledge is very important in cryptography. For instance, in terms of simplifying algorithms for cryptographic protocols, and it can also help in mapping of points between equivalent elliptic curves. You want to map this point to another point in the elliptic curve. Two different elliptic curves. You're given two different elliptic curves and you want to map one point of this elliptic curve A to another point of elliptic curve B. Then you require the knowledge of isomorphism, elliptic curves. Of course, when you want to simplify algorithms for cryptographic protocols, the knowledge of isomorphism of elliptic curves becomes very important. I've also said that elliptic curve cryptography relies on the properties of elliptic curves, including isomorphism. When you're looking at elliptic curve, of course, we'll be looking at that. We'll look at that later. Elliptic curve cryptography. We'll be trying to see how to do encryption and do this decryption of data using elliptic curves. So this knowledge of isomorphism, of course, will be very much relevant in that when it comes to that. Just to ensure that your communication is secure, this knowledge of isomorphism will be very crucial. Now, so I've then included a program that does find out whether elliptic curves are isomorphic. So this is the program that, of course, later on you may want to modify this program where it does a lot of work than what mine is doing. But this way I begin. The function that does the mod, this is exponent. This is exponent. So what this one is doing is, for instance, you're given the base, and you're given the exponent, and you're given the modulus. So what I am talking about is A, and then there's an exponent, some power here, and then mod, let me say P. So this is what this code will be doing. And it's doing this using the fast powering algorithm that we learned. It's doing this using fast powering. So what it's doing, for instance, we talked of U raised to 4. That is what this is doing. And we are doing this mod B, for instance. Then after getting U raised to 4, it's multiplying that by, we'll go to a point where we come up with another function that now multiplies this U raised to 4 by, let me say, A. And then, so this one will also be doing U raised to 6 mod, let me say 11. So this is what this is doing. So just doing modular exponentiation. And it's doing using the fast powering algorithm to do that. So because it has to test whether A prime is the same as U raised to 4 times A. That's what we want to test. And then at the same time, test whether B prime is the same as u raised to 6 times B. So that's what we want to test. So before we do that, we must first of all find what u raised to 4 is, and then what u raised to 6 is. That's what we're doing here. So this is the base, and this is the exponent, and this is the modulus. So supposing the mod is 10, let's just take that as an example. So we are trying our base, we are trying 0, we are trying 1, we are trying 2, all the way up to 9. So that's what this one is doing. It's trying all this. It's trying 0. So it tries 0 raised to 4, tries 1 raised to 4, tries 2 raised to 4, tries 5 raised to 4, and so on up to 9 raised to 4. So that's what is happening in this, what this function is doing here. So it's trying all those, and it wants to see what we get. And then after getting that, then we shall give it a formula of how to pick the u. So we give it a formula that will help us to pick the u for us. Now, so for us to do this exponentiation, I've told it that if the modulus is 1, so supposing we are talking about 2 raised to 4, and we are saying mod 1, that's what I'm talking about. If the mod is 1, then it should return 0. If the modular is 1, then it will return 0. Otherwise, if the modular is not 1, but is another positive value, if it's any other positive value, then we begin by mute the result. So that means our base raised to x mod that p, we say let this result be mutable. Let the result of this be mutable. And initially, we let it be 1. Let the result be mutable. So it will be changing with the time. But we begin by letting it be 1. What about the base? The base, this base will also be changing. It's mutable. Of course, we've said at one point we'll be trying 0, at another point we'll be trying 1, another point you're trying 2, another point you're trying 3, all the way up to 9, if you are dealing with the mod 10. So that's why he's saying it's mutable. So the base will be changing. But then you take that base and divide by the modulus to get the base, Take the existing base divided by the modulus, and then the remainder is what becomes our base. What about the exponent? Is also mutable. The exponent will also be changing. And then so about the exponent, this is why we proceed. While the exponent is not 0, while this power is not 0, you enter this loop. You enter the loop while the exponent is not 0. And so you remain inside the loop until the exponent is 0, and you exit the loop. So when you exit the loop, you will come, what you obtain is the result. What you obtain is the result. When you exit the loop, you come out of that loop with the result. There's something here. Now, here we talked about when the exponent is not 0. So that loop ends here. And then we have exponent greater than or equal to 1. The exponent greater than or equal to 1. So if the exponent is greater than or equal to 1, you perform this. You change the base changes. If the exponent is greater than or equal to 1, the base changes. So how do you change the base? You see, we had the initial base here. The initial base. So if you discover that the exponent is greater than or equal to 1, your new base now becomes the original base squared. The original base squared. Then the result divided by the modulus and write the remainder. So the base will be changing. That's how the base changes, because I've said the base will be mutable, will be mutable. So that is how the base will be changing. Every time the exponent is greater than or equal to 1. So if the exponent is 1, you do that. If the exponent is 2, you do that. Exponent is 3, you do that. And so on, until the exponent becomes 0. So that is how the exponentiation will be done. That is the first function that we require, apart from the main function. Then we have now the function to do to check whether the curve is isomorphic. It's checking the two curves. So this function is checking the two curves. You have curve 1 of the elliptic curve, and then curve 2 of the elliptic curve. So you can see I've just given it the formulas. I've given it the formulas, and I've told it for you in the range, 1 up to p of curve 1, it does this calculation. I don't know whether you can see what I'm reading. I'm saying for you in the range of 1 up to p. So of course, when it's up to p, it understands that it will be doing it up to p minus 1. That's what it understands. So if you give it p to be 10, it knows that then it'll be doing it up to 9. So this is for curve 1. This is for curve 1. So then you tell it, let u be a big unit from this range. Big unit from u. So that it means u is here, this range. Then let u raised to 4. So it's now supposed to calculate u raised to 4, but it will not calculate. It will just ask for it from the mod exponent, function, which is above, which we've looked at above. So it asks for u raised to 4. Then it comes again and asks for u raised to 6 from the same function. That's the function we began with. So that function that we began with has already done u raised to 4 and has done u raised to 6. So this one is just asking what is u raised to 4 and what is u raised to 6 for the first function. Then if now it comes to the second curve. Now this, what is happening here is now just comparison. It's just comparing the left side and the right side. That's what I've written here. If A of the second curve, that's what we call A prime. If A of the second curve equals to u raised to 4 times A of the first curve. I don't know whether you see what I'm referring to. So this is just comparison to try and find if the condition is met. If the condition that A prime is supposed to be u raised to 4 times A. So that is what it's then checking here, that if A of the second curve equals to u raised to 4 times A of the first curve mod p, and then it also checks this, that if B of the second curve equals to u raised to 6, times b of the first curve, then it declares that the u has been obtained. It returns some u. It returns some u. So if it returns that u, it means then the two curves are isomorphic. But if there is no u, none, if there is no such u, then the two curves are not isomorphic. So that is what this code will be doing. So you can see we just give the code the formula and then this condition for checking whether the two curves are isomorphic. So the code will then just be using our formula and then that condition, and it declares two curves are isomorphic or non-isomorphic. Now, of course, we have the main function. This is where we insert our A, our B, and our P. So for instance, the example that I have, my A for the first curve is 7. So I'm talking about y square is x cubed plus 7x plus 11. And the mode I've chosen my P as 17. I'm doing it U32 bits. You can do it 64 bits, 128, and so on. Or even you can do it for very huge numbers. You can do it for very huge numbers. And then I also define the parameters for my second curve. Our A is 7, our B is 6, and then P is still the same P. So I'm talking of y square is x cubed plus 7x, then this time plus 6, and we are doing it mode 17. Then it should print u if that u exists. If a u exists, it must print for me u. And if it doesn't, it must tell me that none exists. There is no u, and therefore the two curves are not isomorphic. But if that u exists, then it must print for me the u and tell me that the curves are isomorphic. So I just want to share the code. We look at it. We see how it runs. And then again, we can try to explain again how it works, just in case there's anybody that did not follow. Of course, I've included the notes for how it works. But let me share it. Okay, this is a curve. Okay, let's run and see. Now it has run. After running, it says that the curves are isomorphic, and of course, it gives us our u. It tells us that u is 4. So that means it has gone through all the process. Of course, it's just doing the same process we used, where it's trying u as 0, tries u to be 1, tries u to be 4, and so on up to u to be p minus 1. And then checks the conditions, the two conditions if they're met. So this is how it does. So there are a few things you can modify on this code. Just ensure that it does more work. A few things you can modify. You can even modify to have it work on big numbers. Like you can see mine is working with U32 bits. You can change that, and you can ask it to do several other things. Okay, I had already explained this, but I can again go through. The first part is just giving us the structure of the elliptic curve. And we understand how the elliptic curve looks like. It will be y square is x cubed plus ax and then plus b mod b, where a and b, a will be coefficient of x and b is a constant. Of course, we know what an elliptic curve is. So we talked of how to test if a curve is elliptic and if it's not. So that means we can test that a curve is elliptic or not elliptic. Now, this part, I'm just explaining the exponentiation function, the modular exponentiation function. We had said mod exponent, base exponent, then modulus. This is how it's written. And we say that initially the result is taken to be 1, but of course this will be mutable. And then the base is supposed to be reduced modulus. So let me just take you back to so that you understand what I'm talking about. Just take you back there. This is that function, the mod exponent function. So this is what I'm explaining. This is what I'm explaining. That initially the result is taken to be 1. And of course is mutable, to be changing from time to time. Then the base has to be reduced modulus. Of course, again, that will be changing from time to time to be mutable. Then the exponent, we proceed to the loop. So that is where I was explained in my notes. That is it. If the exponent is greater than 0, you enter the loop. Now, I've said that if the least significant bit of the exponent is 1, multiply the result by base modulus, then you square the base, then shift the exponent. Just take you where the code is, so you understand what I'm talking about. Okay, this is where I'm referring to. If the exponent is not 0, the exponent is not 0. So if this, when do we say that something is not 0? So, and of course, we're only focusing on the positive part. You're not interested with the negative part because we are doing modulus. So that means the exponent is greater than 0. If it's not 0, then it's greater than 0. That's what it means. So if it's greater than 0, if the exponent is greater than 0, you enter this loop. And then the last part, it was talking about this, that when we, at the end of it, the base will be squared, then reduced to modulus. That is what that part means. But you'll go through those notes later, slowly by slowly, and as you create your own code and modify your code to see whether you can obtain several functions out of this same code. Any question? Mulwa. Owen?
Not much anything.
Yes, Owen, I cannot hear.
I'm saying, I hope you can hear me.
I cannot hear you well. I don't know. There's some.
Um, I think I have problems in the microphone.
Lynette, can you hear what Owen is saying? Or it's you've written on the chat, huh? Oh, Lynette says Owen is not clear. Owen, we cannot hear. I cannot hear what you're saying. Maybe you can write on the chat. Simon?
Yes.
Yes, any question?
Don't have any question for now, Martin.
Okay.
Okay.
Okay, let me look for another code that I wanted to share. I have not included it here, but I wanted to share it. Just a minute as I wait to see what Owen was talking about. We check for. Just a minute. I'm trying to check. Okay. Owen, have you written? Yes, I did not get, or you're saying you have no question. I did not hear you. Yeah, there's something I wanted to look at on not really isomorphism, but related to it, and that's what I'm looking at. Just a minute. I just my program is taking time to run. Basically what I wanted to show is the next thing that we'll be looking at that is slightly related to isomorphism, but not the isomorphism itself. I'm not seeing where it is actually. I think what I'll do is I'll share it. Once I get it, I'll share it. And then we begin from there when we meet next time. Because I'm trying to locate it and I can't see where it is. So I think we should just end here. And then I'll share it later with the notes. When I say this is all right, you have understood everything. I think I have problems with my microphone. Okay, it's okay. Now, so I think we should end here. Then once I locate where I put that program, I'll then share it. Then we begin with it in our physical class, which will be on Thursday in the lab. The one we'll be having in the lab on Thursday from noon. Of course, but I will get confirmation from Alex if we'll be having that our boot camp. I don't know whether Alex is around, or maybe he'll communicate later. Alex.
Oh, Alex is not around.
Okay.
So I was the one who was running the session today.
It's okay.
Yeah, but maybe he'll communicate through WhatsApp.
It's okay.
Okay,
So
okay,
I think then once we get that communication, then we see what to do. If we'll be having of course I know we'll be having it, but it'll just have to confirm. Okay, thank you.